First of all, I would like to thank the organizers for this huge effort they are taking every year. And from my side, I must tell you that I look forward to Februaries of every year now. So I hope this continues forever. So that's the title of my talk. I'm going to talk about the random field Ising model, a very popular model in statistical physics. And this time it is with conserved kinetics. So the brief outline of the talk, first an introduction to the random field Ising model with conserved kinetics. Then some of the consequences because of the conserved kinetics are super-universality violations, different kinds of growth laws, and finally, if I have the time, I'll tell you a little bit about this very nice generalized stomata sum rule that we've discovered while doing this work. So the work is done with Manoj, who is a graduate student, and Sanjay Puri from JNU in New Delhi. So that's the Hamiltonian for the random field Ising model. It's a very prototypical example of a system with Quench disorder. So as one can see, this is the part which promotes ordering, and that's a field that you add at every site to bring in the disorder. So these are Ising spins. SI takes values plus minus 1, and as I just mentioned, interaction J prefers a magnetized structure, and HIs are the disordering fields. You can draw them from various distributions, but usually people draw them from a Gaussian distribution. It could be a bimodal distribution, it could be a uniform distribution, and so on and so forth. Now, the random field Ising model in 2D does not exhibit a non-trivial phase transition. There's a phase transition at delta equal to 0. Now, in this case, delta, the variance of the distribution, is a measure of the disorder in the system. So you can tune in the order-disorder transition by varying the disorder strength delta. But in d equal to 3, there's a small region of the T delta plane where the equilibrium state is ferromagnetic. So you could have a transition from ferro to para in this case. And when delta is equal to 0, Tc is something like 4.5. And when T is equal to 0, that is if you're on the disorder axis, delta C is 2.28. So these are a few experimental realizations of the RFIM, which is why it is a rather popular model. Okay. Diluted antiferromagnets in a uniform field. These are realizations of the RFIM. Dipolar quantum magnet, lithium, holmium, yttrium fluoride. That's also a realization of the RFIM. And binary mixtures of the kind AB in porous medium, they are also represented by the RFIM. So this AB could be an oil-water mixture, it could be a colloid polymer mixture, some of the things that we have been hearing since the morning. So now, since these spins do not have an intrinsic dynamics, one has to put them in contact with the heat bath to generate the stochastic spin flips. So that's what gives you the Glauber model with non-conserved kinetics. So the DAFs and systems like lithium, holmium, yttrium fluoride, these are mimicked by the Glauber model with non-conserved kinetics. And systems like the binary mixture, one has to introduce the dynamics using the Kawasaki spin exchange model. Okay? So here the order parameter is conserved, okay? Naturally because the number of A atoms and the number of B atoms are conserved, so this is a conserved dynamics. Okay? And the other important thing is that although the two models describe different time-dependent behaviors, the equilibrium state here is unique. So that's my first set of results. This is domain growth after a temperature quench. Okay? So that's domain growth in d equal to 3 C-RFIM. Now the C is referring to the conserved dynamics. Okay? That's delta equal to 1.0, which is the ordered phase. So we've quenched the system in the ordered phase. Okay? Or rather, we expect order in this particular system. And the temperature is 2, which is less than Tc, which was about 4.5. So these are two snapshots as the time evolves. So as one can see, there's formation of order here. The green spins are corresponding to SI equal to +1. blue are corresponding to SI equal to -1. So one can also see what happens if we have a different disorder. Okay? So this is the case with disorder equal to 2. Okay? So that's a larger disorder. And one can see that the interfaces in the two situations, they are different. In one case, the disorder introduces fractal, rough interfaces, which we show later that they are fractal. Okay? And if the disorder is small, this roughness is not so significant. Okay? So one way to characterize morphologies is by evaluating the correlation function. Okay? So that's the standard definition of a correlation function. One typically defines a correlation length in this case. That's the distance over which CR decays to some typical value, let's say something like 0.2, but that's not very important. Okay? And what is crucial here is the connect with the structure factor. The structure factor is what is measured in small angle scattering experiments. So this is nothing but the Fourier transform of the correlation function. So these are the two tools that we keep using to characterize our morphologies. So that's the plot showing dynamical scaling. What it is showing is the scaled correlation function for a particular value of delta. Let's say this is delta equal to 1.0, and this is at different values of t, so as the system is evolving. So, we've let the system evolve really for very, very long times. This is one of, it was a very challenging simulation. Okay? And in this case, L of t, the characteristic length scale, is the first zero crossing of CRT. Now, this is a typical correlation function plot for a system with conserved dynamics. If it's a non-conserved dynamics, you don't have this little negative part in the correlation function. Okay? So as one can see, there's a collapse of the dynamical, there's a collapse of the correlation function for different values of t, and that's a signature of dynamical scaling, and it's an indication that the morphologies are characterized by a unique length scale, even though time is evolving. However, if we fix the time and look at different values of delta, one sees that there is, they don't collapse onto a master curve, okay? And which indicates that the scaling function is not robust with respect to disorder. Okay? So that's what one calls as the super-universality violation, because if the system is invariant to the amount of disorder you have, you call it super-universality. And there are many versions of, in fact, the RFIM with non-conserved dynamics has been treated as, people have observed that it's a it obeys super-universality. So here I plot I look at the growth laws. So I look at L of t as a function of t. So that's the plot of the characteristic length scale on a log-log scale. And pure systems generally obey this particular very well-known growth law, which is the Lifshitz-Lyuzov law. It says that L of t goes as t raised to 1/3. Okay, so that's for delta equal to 0. And that's the line that we have here. Now what one observes in the RFIM, it's a disordered system. So there's slowing down of domain growth at late times for higher values of delta. There's algebraic growth at early times. Okay, so that's a straight line here, which means that L of t goes as t raised to 1/z. Now this z is a disorder dependent exponent, okay, which we will derive in a very short while. And this is also something that we show, that the crossover, it's not a correction, mind you. As time evolves, the growth goes from algebraic laws to logarithmic domain growth. Okay? And so that's the typical form of L of t that we will derive if there's time. Okay? And this exponent phi is what is usually called as the disorder, it's called as the barrier exponent. Okay? So now the job at hand is to determine these different exponents, that's z bar and phi. Okay? So for this I have, oops, it's only 2 minutes now. So for this I have a scaling ansatz. Okay? So this is something which has been recently floating around in the literature given by Corbery et al. Okay? So they give a scaling ansatz by which one can find out this. So L of t goes as t raised to 1/z effective. Okay? And they have a formulation by which you can find out the effective z exponent. And that is what, so the effective Z exponent, as one can see, involves a delta ln t by delta ln L. So it's a derivative of the growth law that I showed in the previous slide. So that's what one does over here. So this is a plot of t ln L over t ln t, and inverse of this on a semi-log plot. Okay. So the dashed line is the disorder dependent exponent, Z bar of the power law, algebraic power law, and this is followed by a late regime where Z effective is time dependent. Okay. So then you do more of the machinery, and it's possible to find out what is this deviation that is happening at late times. Okay. And that's another fit. So it tells us that Z bar minus Z effective is given by this particular form, and it helps us to evaluate this very important exponent phi, which is the barrier exponent. Okay. So that's the data collapse on getting all these exponents. So Z bar is dependent on the disorder, so these are the different these are the different values of the exponent, and that's what has happened to this data by doing an appropriate, because of you using this appropriate scaling function. And let me just tell you why is one talking about logarithmic growth here. Okay. So if I go back to the equation I had put in, that's equation 4, okay, which I had put in to evaluate the Z effective. Okay. We make this substitution of, I think maybe I should just go back over here. So that's the equation I'm looking at now. Okay. So I know what is the form of Z effective minus Z, and that helps me to evaluate what is G of Y. Okay. So this G of Y, if I invert it, I get, I get the expression for the length scale, and the length scale has a dependence on log of t. Okay? So so that's the asymptotic growth law form which emerges from the scaling theory. Okay? And this has a lot of physical significance because domain growth in disordered systems, it proceeds via activation over barriers. Okay? And the energy of the barrier, it goes as L raised to phi. Okay? So that's an important quantity to evaluate, which we have been able to evaluate in by using the scaling protocol. Okay? And of course, once again, I emphasize that it gives rise to this particular logarithmic scaling, and this is discussed in the classic papers of Hughes and Henley and Lai, Mazenko, and Valls. Okay? So I will not go through these rough interfaces and non-Porod tails that we've been looking at, and let me just come to my summary. So what we have here is comprehensive MC simulations of domain growth in the RFIM with conserved dynamics and in d equal to 3, because that's where you get the non-trivial dynamics. And one can observe clean crossovers from disorder dependent power laws to a growth independent, to a disorder independent logarithmic growth. Okay? And there's dynamical scaling, which signifies the presence of a unique length scale. However, super-universality is violated in these systems, so the system is not robust to the presence of disorder. And although I did not discuss this, let me just tell you what I planned to discuss. The small r behavior of the correlation function, it exhibits what is called as a cusp singularity. And the cusp exponent yields the fractal dimension of an interface. Okay? So one can evaluate the fractal dimensionality of the interfaces separating the up and down regions of the ferromagnet. Okay? And the corresponding structure factor, so if this happens in the small r region, it gets reflected in the tail of the structure factor. Okay? So the structure factor exhibits a non-Porod decay. Okay? So that's the form of the structure factor that one usually sees. And that's a signature, so this is what is measured in experiments. And that's a signature of scattering of fractal interfaces. Okay? And we found that, and people always want to give mathematical forms to these structure factors. Okay? So for some kinds of structure factors, they have been given, there have been mathematical forms. The very well-known one is the OJK function or the Ohta-Jasno-Kawasaki function. But for this particular case, there's no mathematical functional form. So we have a sum rule which the structure factor should satisfy. And if you don't know the exact function, it's always nice to have other ways of arriving at certain special features of things like the structure factor and the correlation function. So that's what the generalized Tomita rule that we've derived gives us. So with this said.
Self-averaging and non-self-averaging cases when you have disorder.
As you can see, our crossovers are very, very clean. Okay? So we had to do a lot of self-averaging, a lot of disorder averaging to get these results. Okay? And if your system size is small, then these crossovers are not very clean. So this was the first doable largest system where one could get very clean data. And of course, the larger the system size, the better it is, but already we've gone very late into times. And as a matter of fact, this is one of the first lattice model studies of conserved RFI.
Is there any Harris criteria for this system, and does it have any effect on this growth?
I actually don't understand your question.
No, I mean, so there is this Harris criteria, right? Whether the clean critical exponents are still valid or not. I mean, even in the presence of.
I don't know if it is. We've not checked any of that. Numerics indicated the clean crossovers, and the scaling collapses were what gave us confidence in making such statements.
Close this session.